Welcome to today's ITC Colloquium. It's my pleasure today to introduce Gianfranco Bertone. Gianfranco is a professor of theoretical astroparticle physics at the Gravitational Institute, which is Gravitational Astroparticle Physics in Amsterdam, and a leading figure in dark matter research. He leads an ERC advanced grant-funded program named dynamical, which is a very nice name. Focused on developing theoretical and computational models to identify dark matter imprints in gravitational wave signals. And it's also, I believe, the topic of today's talk. And also, Gianfranco played a central role in building major European initiatives in astroparticle physics. He's also, as you will see, very active in science outreach, founded the Cosmos Initiative, Prize Initiative, which is now a UNESCO-endorsed global program promoting science literacy, and I think you will discuss this introduction. And so please join me in welcoming Gianfranco.
Thank you. Thanks, Fabio. All right. Thanks a lot for the invitation. It's always a pleasure to be here. Today I would like to tell you about this new field of research, which is gravitation, how to use gravitational waves to probe the nature of dark matter. And what I would like to do is to start with a very kind of broad but brief prologue on the dark matter narrative, or what is that we talk about when we talk about dark matter. Then I would like to say a few words about what is that we've learned about the nature, the identity of dark matter so far, with all the observations and experiments we have performed over the past 4.5 decades, basically, since we have evidence of dark matter. And then I will move hopefully quickly to the second part, which is what I really want to focus on, which is how we can use gravitational waves to probe the nature of dark matter. So in this kind of prologue, I wanted to start with something you probably all have heard about in one version or another of this, which is what I refer to as the dark matter mythology. So if anyone presents at a conference the history of dark matter, usually this is not even mentioned. But if people do that, they will only say basically two things about the nature of about the discovery of dark matter, the fact that Fritz Zwicky in 1933 coined the term dark matter in his paper on the coma cluster, and that Verhoeven in the 1970s discovered dark matter with rotation curves. But what I want to the message I want to convey today is that the history is way more interesting and nuanced than that. And my starting point was, my interest in the history of dark matter was actually triggered by reading this paper here. This is a paper by Fritz Zwicky, Fritz Zwicky wrote in 1933, but this is not the famous coma cluster paper. This is a paper on cosmic rays. How far do cosmic rays travel was the question back then. So this is 1933, so we didn't even know that. People thought that cosmic rays might even be photons, as a matter of fact. They were trying to figure out what the origin of these mysterious cosmic rays was. And then, so this is a few months before the coma cluster. He writes this. Let me make it a bit bigger for you. He writes, now, according to the present estimates, the average density of dark matter in our galaxy and throughout the rest of the universe are in the ratio basically exceeding 10 to the 5. Okay? So clearly, the 1933 paper was not the place where he coined the term dark matter. Dark matter was, a concept that existed in the literature. Not only it existed, but there were estimates of the local density and the average density in the universe of dark matter. If you think about this, this is a bit, this was shocking to me because this is only a few years after the discovery of the expansion of the universe, right? And already people had an estimate of the average density of dark matter and also the average density, or the local density and the average density in the universe. So I don't have time today to go through the history of dark matter, but I just wanted to say that already back in 1904, there were people like Lord Kelvin who applied his own kinetic theory of gases to the study of the universe. In particular, he wanted to associate the velocity dispersion of galaxies in the universe back then were basically the stars of the Milky Way, with the density of matter. And he argued that many of our stars, perhaps a great majority of them, may be dark bodies. Then Henri Poincaré reflected on this, used the term matière noire, first in French, then in English, dark matter. And then one can say, well, maybe Zwicky was the first one to apply the virial theorem to clusters of galaxies. There was another scientist, a very well-known scientist, who actually applied the virial theorem like 12 years before Zwicky to an astrophysical system. Albert Einstein in 1921 applied the virial theorem not to a cluster of galaxies, but to a star cluster. And he concluded he was looking for something completely different. He was looking for evidence for the cosmological constant. But then he concluded that the non-luminous masses contribute no higher order of magnitude to the total mass than the luminous masses. So in other words, he obtained an upper limit on the abundance of dark matter in these systems. And it's only much later that Fritz Zwicky performed his famous work on velocity dispersion of galaxies in clusters. Anyway, so the story is very rich, very interesting. If you're interested, there is a paper called A History of Dark Matter that I wrote with another physicist, with Dan Hooper. And there's also some work that we did with professional historians of science, in particular Jeroen van Dongen. He's a professor in the history of science at the University of Amsterdam. And this is Jaco de Zwart, a brilliant PhD student who worked with Jeroen and myself on the history of dark matter. He moved then to MIT, and now he's in Cambridge, and he's working on a book on the history of dark matter. So this might be a good starting point in case you have an interest in that. But let me move on something which is more relevant with what I want to discuss today, which is this other visualization that we typically see at conferences and that we use to say there's more in the universe than meets the eye. And in particular, the argument is basically that the universe, if you consider observations that range from subgalactic scales all the way to galactic, clusters of galaxies, all the way to cosmological scales, so any observation you can really perform in the universe. And if you insist that the theory of gravity you want to use is general relativity, then the matter energy budget of the universe is completely dominated by dark energy, and there is 27% is in the form of dark matter and only 5% of atoms. But what I want to stress is that there's nothing fundamental about this 95-to-5 ratio. This is sometimes referred to as the ratio between knowledge and ignorance in the universe. But I think it's really an overstatement. And the reason for that is that if you look at different scales of space and time, you get a completely different picture, of course. If you draw a sphere around the Earth and ask the question, what is the matter-energy budget inside this sphere? Well, this is completely dominated by baryons, by 24 orders of magnitude, in fact. The local density of dark matter is believed to be of order 0.4 GeV per centimeter cube, and that turns out to be, Zwicky was actually right in his estimates, is about 10 to the 5 times the average density of dark matter in the universe. If you draw a 20 kiloparsec radius sphere around the center of the Milky Way, then you start to pick up the contribution of dark matter. And now in particular, if you use Gaia data, you can infer what is the relative proportion between baryonic matter and dark matter in this sphere. And it turns out that this cosmic pie looks like this. 72% of the matter is in the form of dark matter. The rest is in the form of atoms. It's only when you go on very, very large scales, on scales larger than clusters of galaxies, that you recover this relative proportion between dark matter, dark energy, and atoms. So if you're interested in understanding the nature of dark matter, you really have to keep in mind that, drawing the matter and energy budget of the universe on the largest scales doesn't necessarily capture, all the information you're interested in. And even more compelling, I think, if you ask the question, when is that true? When the particular distribution of dark matter, dark energy, and matter applies? Well, this only applies now in the history of the universe. If you look back at Big Bang nucleosynthesis and ask the question, what is the universe made of? Well, it's almost completely dominated by radiation. So neutrinos and photons, relativistic particles, basically. Then universe expands, radiation gets very quickly diluted, and if you ask the question at recombination right after matter-radiation equality, and you see that matter is starting to dominate the energy budget of the universe. Dark matter and atoms, the relative proportion remains more or less constant throughout the history of the universe, and you see that radiation is being diluted away. Today, you have this relative contribution, and if it's true that dark energy is something like a cosmological constant, if you will ask the question, if cosmologists in the distant future will ask the question, what is the universe made of? They will come up with a universe which is essentially made 100% of dark energy in that case. Okay, so how do we make sense of all of this? So typically there are many ways of doing that, depending if you're like a theorist, an observer, or a person running numerical simulations of the universe. But I think what's really like a very compelling way of saying, the standard model of cosmology is capturing something really fundamental about how the universe behaves, is that if you take a supercomputer, give us initial conditions, the CMB, basically the inhomogeneities that you see imprinted in the CMB, and then evolve the universe in presence of dark matter and dark energy, admittedly including some subgrid physics, on scales that you can't really completely resolve with your simulation, start to produce a universe that very much looks like the universe we observe, and not just visually, but also in terms of correlations, spatial and angular correlations in the distribution of galaxies, types of galaxies you form, chemical enrichment of the interstellar medium, and so on and so forth. If you ask the question, how is dark matter distributed in these systems, there's a very well-known paper in 1996 where we started to have a pretty decent idea of how dark matter is distributed in all these virialized halos. And the quite surprising result back then was that no matter what halo you look at, from dwarf galaxies to galaxies all the way to clusters of galaxies, any virialized halo has a sort of a universal kind of profile, of density profile, as a function of the distance from the center of these halos. It goes like r to the minus 1 in the inner parts, goes like r to the minus 3 in the outer parts. And this is what is referred to as the Navarro-Franken-Weiss profile, which I will mention later on. Now, of course, we made a lot of progress in numerical simulations. If you ask the questions, so this was done with simulations with only dark matter in them. Now we can include baryons. If you ask the questions, in all the galaxies that you form in numerical simulations that look like the Milky Way, the so-called Milky Way analogs, looking like the Milky Way in terms of rotation curve, in terms of bulge to disk ratio, thickness of the disk, all the observational quantities you can think of and that you can extract from simulations and compare with data about the Milky Way. You see, if the black line is the NFW profile, the Navarro-Franken-Weiss profile, what you get in simulations is actually a bit more complicated. The overall structure is more or less the same. You always have this increase in the profile towards the innermost regions of the galaxy. But depending on the history of your galaxy, on the merger history, and in particular on the star formation history of your galaxy, you can have profiles that are more dense or less dense in the inner parts than what predicted by the NFW profile. So the general trend is preserved in these simulations, but the details of how steep the profile is in the inner regions depends on the details, depends on the history of the galaxy you consider. Now, we've established, we've reviewed the distribution of dark matter in the universe, which is a central ingredient of what I will discuss in the second part of the talk. Let me say a few words about what is that we've learned about the nature of dark matter in the past 4.5 decades. Now, a lot of work went into the identification of dark matter. If you ask the question, if I have a particular dark matter candidate in mind, a particle that might explain the dark matter in the universe, what are the properties that this new particle would have to satisfy in order to be considered a good dark matter candidate? Well, you will have to make sure that it passes this 10-point test. I will not go through it in any detail, but let me just mention that, first and foremost, your particle, the particle that you have in mind, must be able to you must have a mechanism in mind to produce the particular particle in the early universe with an abundance that matches the observed abundance of dark matter today. And that abundance is known with a precision of a few percent, thanks to CMB observations. Okay? You know that your dark matter particle must be cold, and cold can be made very precise. There's just a statement about the free streaming lengths, or these particles must be non-relativistic at the epoch of structure formation. It must be neutral, so no electric charge, no color, nothing that couples these particles significantly with the particles of the standard model. Must be consistent with Big Bang nucleosynthesis, so no relativistic degrees of freedom. Must be consistent with stars, stellar structure, and evolution. It's very difficult, actually, to postulate the existence of a new particle in the universe without destroying something, destroying stars or unbound dark matter halos and so on. And then this bottom row is a statement about the interactions of these dark matter particles with themselves, with baryons, and also the self. So this is self-scattering, let's say. This is a constraint on the self-annihilation into photons or other astrophysical fluxes like neutrinos, antimatter, and so on. There's 10 points in this in this test, which is more philosophical than physical, which is that you want to have at least in theory, at least conceptually, a type of experiment that you can perform to detect the candidate that you have in mind, right? This is essential, really, to enable science, really, because otherwise the game can be, how can I hide my particle to any experiment that I can ever perform? And actually, even if the couplings are only gravitationally, there are ways of testing these candidates. So where does this leave us? The list of dark matter candidates is, almost endless. There are more candidates than there are particle physicists, I would say, because many have worked on on different dark matter candidates each. So how do we make sense of all of that? Well, this is, instead of going one by one through all possible candidates, we've tried in this mind map to organize the information about what is the possible nature of dark matter. So if we only consider the three, let's say, order 1 blobs here, light bosons, neutrinos, and weak scale, these three up here, these are the so-called natural candidates, where by natural, what we mean is that these candidates have not been proposed to explain dark matter, but they arise from theories that were postulated for completely different reasons, right? So the prototypical example here is the QCD axion that was postulated to solve the strong CP problem in quantum chromodynamics. A lot of physicists are interested in the neutrino sector, completing the neutrino sector. And in the case of the weak scale, there's been a huge effort to try to understand the so-called hierarchy problem, why the weak scale in particle physics is so different from the scale of gravity, for example. And in the context of these theories, typically at the end of the 1970s, beginning of the 1980s, physicists working on these candidates realized that their theories predicted the existence of particles that would be perfect dark matter candidates. Okay, and this has triggered a huge interest, really, in all of these candidates. There is also another possibility. Dark matter can be made of other particles, and you can decide to have a completely different approach. You can say, I don't care about the big problems in theoretical physics. I want to solve the dark matter problem. So you take your standard model of particle physics, and you try to extend it. Take the Lagrangian of the standard model that describes the particle physics content and interactions of your theory, and just extend it to add the terms that only explain dark matter, right? And then you hope eventually that this can be embedded in one of these, overarching theories. So people have played this game too, and there are many examples of, of this type of approach. But just for completeness, let me mention 2 other possibilities. One possibility is that dark matter is not made of, elementary particles, but is something more macroscopic. And the prototypical example here is primordial black holes. You know, the black holes cannot, astrophysical black holes cannot be the dark matter because, you know, dark matter must exist way before astrophysical black holes are formed. But primordial black holes might be, are good, in principle, good candidates. And in fact, it's one of the first candidates that have been proposed by people like Stephen Hawking and many others in the early 1970s. And then there is this kind of elephant in the room. You know, as I said, you know, all the evidence we have for dark matter comes from the fact that we insist that general relativity is the right theory of gravity on all scales in the universe, right? But there's no guarantee that that's true. You can decide to, you know, follow a completely complementary approach. You can say, what I'm sure of is that the standard model of particle physics works very well. You know, you can explain all observations you've ever, you can explain all experiments we've ever performed in our laboratories with the standard model of particle physics. So you can say, well, let me try and modify GR instead and stick to my, the model that I have for matter. There are huge difficulties associated with that. It's extremely difficult to modify GR without, you know, ruining the agreement with something in the universe. And I would say that, you know, we can't completely rule out the possibility that the explanation for dark matter must be found in terms of modified gravity. The best we can do is to try and identify these particles, to measure these particles in our laboratories, because this would tell us that this is not the right approach. For those of you who have an interest in modified gravity, let me just mention that the universe really seems to behave like GR plus the standard model of particle physics plus one species of cold and collisionless particles. All right? So that doesn't mean that cold and collisionless particles exist, you know, but if you're looking at you're interested in an explanation in terms of modified gravity, well, your theory must reduce to this kind of model at all scales in the universe. Okay, so I'll stop there because we don't have much time to discuss that. If you're interested, just let me know. The only other thing I wanted to say about the identity of dark matter is that the previous mind map is useful to, at least at that conceptual level, to understand what are the possible ways of attacking the dark matter problem. But I think it hides something quite interesting and surprising, I would say, about the huge uncertainty on the mass of the dark matter candidates. So if you look at all those theories, or all those models that we discussed, and you organize them around, in terms of mass, you see that for wave dark matter candidate or fuzzy dark matter candidates, the mass can go down, the mass of the elementary particle can go down to 10 to the minus 20 electron volts. Okay? On the opposite side of the spectrum of mass, you can have primordial black holes with a mass of 10 or 100 solar masses. If you convert that into GeVs or electron volts, that's around, it's more than 10 to the 70 electron volts. So this is an uncertainty over 90 orders of magnitude, 90 orders of magnitude, on something as fundamental to cosmology as the mass of the dark matter particle. Okay, so this is a huge, huge problem for cosmology. It lies really at the heart of cosmology, and I think we should do our best to try and at least narrow down the range of possibilities and hopefully to identify the dark matter. Okay, so what we've done in the past few decades was to essentially focus on a subset of candidates in view of this uncertainty. You can't build one experiment to search for something that could have an associated wavelength the size of a galaxy or be a primordial black hole with a mass of 100 solar masses. Right? If you want to search for a particular candidate, you need to be smart about how you do it. And what we've done in the past was to focus on a subset of possibilities and probe as deep as we can. And because of the interest in particular that these theories at, at the weak scale in particle physics have prompted, people have started to search for these weakly interacting massive particles at colliders with underground experiments and with astronomical observations. But none of these experiments has ever found any evidence for dark matter and for the existence of these WIMPs. At colliders, we managed to set lower limits on the mass of the dark matter particle, the potential dark matter candidate. And the argument is quite simple. You have a certain center of mass energy in your collider. These particles might exist at energies that you haven't yet achieved in particle colliders, but you can rule out all particles below a certain mass, because otherwise you should have seen them. And similarly, with direct detection experiments and indirect detection experiments, you can rule out combinations of cross-sections and masses that would have produced a result in your experiments, but because all you've seen is consistent with backgrounds, you can rule out those combinations. So exclusion plots ruling out everything above certain lines, essentially. Now, if you ask the question, where are the WIMPs, and even more explicitly, are WIMPs ruled out as dark matter candidates? Well, my answer to this question is no. And so the kind of order zero argument is that for the moment we have absence of evidence for these candidates, but that's very different from having evidence of absence. Right? These are two completely different concepts. We might get here to the evidence of absence, but only under some assumptions about what these WIMPs might be. So for instance, some assumptions about whether they are supersymmetric particles or particles arising from universal extra dimensions, and so on. So it's true that we have ruled out a lot of the parameter space. Ruling out completely the idea of a WIMP is way more difficult, and we need to keep this in mind as we go forward. And also have some more kind of technical arguments if you're interested in that. But what I wanted to do is instead moving on to the second part of the talk. And now that we have reviewed, what is it we know about the distribution of dark matter and about the possible nature of dark matter, I want to ask the question, how do we move forward in view of the absence of evidence for the leading candidates? And in this paper here that I wrote with a colleague who has UC Irvine, Team Tays, we've argued that we have at least 3 different strategies. The first one is to broaden, improve, and diversify the searches that we perform, the lab searches that we perform for dark matter. And this is already happening actually in the community. There's a lot of very interesting new ideas about the kind of experiments and the kind of technologies that we can develop for searching for dark matter. The second strategy is to exploit astronomical and cosmological observations, right? We've been guided in our exploration of the nature of dark matter by what I would call our theoretical prejudice on what we thought the most interesting candidates were. I think it's really time to go back to really and ask the fundamental questions. Dark matter is a problem that arises from cosmology, really, from astronomy and cosmology. And now we have amazing surveys that are taking data. So it's really time to ask, go back and ask the key questions. Is dark matter really cold? Is it collisionless? Is there any evidence of, self-interactions or couplings with other things in the universe? How is it distributed in the universe, and so on? And again, there's a lot of activity on that front too. But what I want to focus on in today's presentation is how we can use gravitational waves to probe the nature of dark matter. All right? So this is what I will focus on in the rest of the talk. Now, before I discuss the technical details, let me just mention that all the results, I will show the technical results that I will show, were obtained by this wonderful team of young people, and I'll try to give them proper credit as I go through all of these technical results. So these are previous and current members of my team in Amsterdam. Now let me start from the basics. why gravitational waves? You know, this might seem really a kind of a strange approach to dark matter, right? Gravitational waves are a typically strong field phenomenon, right? You know, they arise in the limit where the gravitational field is as strong as possible in the universe, which is around black holes. Dark matter, the evidence for dark matter, sorry. The evidence for dark matter typically arises in the opposite regime, in the very weak field, you know, typically in the outskirts of galaxies and so on. So why are we even talking about this? Well, consider the following. You know that we have ground-based experiments that since the end of 2015 are detecting the gravitational waves directly. So experiments like LIGO, Virgo, and CAGRA. You know that the announcement of the first detection was in early 2016. Nobel Prize for this first detection was in 2017. Now we have hundreds of detections of events, and because of the size of these experiments, you're sensitive to certain frequencies and time scales that typically correspond to the merger of stellar mass black holes, okay, which is, you know, what we typically observe in these interferometers. At much smaller frequencies, we also know that we have pulsar timing arrays, and I'm sure you've all heard about the stochastic backgrounds as detected. That was detected by nanograph and also with contributions from other pulsar timing arrays. Okay, so when you decrease the frequency, you become more sensitive to way more massive black holes. And in between, you know, many of us are working on the new interferometer, the space interferometer LISA, the laser interferometer space antenna that should be launched by the European Space Agency in 2035 with, you know, the buckets of sensitivity around millihertz. And again, this corresponds to supermassive black holes. Now, why am I saying this? Because if you think about it, these supermassive black holes, you know, these monsters that reside at the center of galaxies, they reside in very dense environments, right? You know, these are some of the most dense environments in the universe, as a matter of fact. There's a lot of baryons, a lot of gas, lots of stars, and lots of dark matter, as a matter of fact, around these objects. Okay, so let's talk about these black hole environments. What do we know about black hole environments? Well, we know from GR, we know that black holes are completely described by mass, angular momentum, and charge. We also know that real black holes do not exist in vacuum. And in fact, it is the environment of the black hole that determines the history, the formation and merger history of the black holes. And in fact, the probability of measuring a particular mass, particular angular momentum, charge, and distance or redshift actually crucially depends on the environment. The very fact that we consider Q equals 0, charge to be 0 for these objects, is because they are embedded in an astrophysical plasma. The other point I wanted to make is that these environments enable electromagnetic detection in the first place. If we can produce images like this one with the Event Horizon Telescope, it's because we have baryons, accretion disks around black holes. And the point which is less explored, and what I want to focus on today, is how these environments affect the production of gravitational waves, and in particular, the details of the waveforms that are produced by objects merging with these black holes in these environments. We will consider 3 different types of environments. So if someone who's risk averse, likes to play safe, you can think of an accretion disk. Accretion disks are observed and known to exist in the universe. So we know that we need to include this possibility in our calculations. You can also decide to be what I call here a radical conservative, right? And this is in the same sense as John Wheeler was using this term, which is to say you can be conservative in the sense of deciding you want to trust your theory, that your theory is correct, but you can do this in a radical way. And you can ask the question, how far can I extrapolate my models, in terms of range of distances over which your model is assumed to be correct. And then if you validate, if you find that your model works on those scales, well, you enormously extended the validity of your model, the range of validity of your model. If it breaks, well, you know something about your model, about the range of validity of your model. And I will discuss in particular these overdensities of dark matter that you would predict naturally around black holes in this context. You can also decide to be speculative. You can say, well, I'm interested in things like string theory, and I know that in these theories, I predict the existence of ultralight particles. These ultralight particles might have de Broglie wavelength, which are associated with the de Broglie wavelength, that are on astrophysical scales, so as big of the size of black holes, or in principle even higher. And it's been known for many, many years, since the work of Seldovich and Hawking and many others, that you can produce super radiant clouds around black holes when the wavelength associated to the dark matter particle, or the particle that you have in mind, is comparable with the size of the black hole itself. Okay, so there's a huge community of people who are interested in this possibility. So what happens, what do we know about the dark matter distribution around black holes? Well, what happens when these black holes grow? You can ask the question, suppose that there is a small seed black hole at the center of your galaxy, and this black hole grows in mass, and you ask the question, how does the distribution of dark matter particles, or cold and collisionless particles, change when the black hole grows in mass? You can do the simple exercise for a two-body system. You can imagine, growing the mass of the sun on very long scales, on adiabatic time scales, compared to the orbital period of the Earth around it, and you will see that the orbit would shrink, responding to the increased gravitational potential. You can do the same in a more sophisticated way for a distribution of particles. If the growth of a black hole is slow, you conserve the adiabatic invariance, and you can demonstrate actually that if you have an initial power law distribution of collisionless particles around the black holes, the final distribution is again a power law, but with a different slope. Okay, the power law index actually can be derived analytically under certain assumptions, and so for instance, if you plug, if gamma is the initial slope of the dark matter profile, and gamma spike is the final one, you see that if you substitute 1, as in the NFW profile, you get something which is of order 7/3 here. Okay, so you go from -1 to -2.3 in that case. And this is something that many people have worked on since the pioneering work of Peebles and many others in the 1970s and 80s. This was applied to the case of dark matter particle by Gondol and Silk in 2000, and they've shown that if you start from something which is NFW initially, then within the radius of gravitational influence of the central black hole, you change the slope of the dark matter profile. Now, gravity is a scale-free problem, but there are two obvious scales in this problem. One is the size of the horizon of the black hole, or the ISCO, the innermost stable circular orbit, below which you cannot have stable orbits. There's another scale here which determines where the change in slope happens, which is the radius of gravitational influence of the black hole, right? Past a certain point, if you grow the mass of the black hole, particles don't even notice that this is happening because there's so much else contributing to the gravitational potential. Okay, so this is the prediction we've had the only prediction we've had for a long time, both by Gondol and Silk, and there was, I forgot to add reference, there was a relativistic extension of this calculation. Now, recently we have extended this to a more kind of physical way of doing things. There was an assumption in the previous derivation, which is not really very physical, which is that a black hole grows from a a zero mass, right? And no black hole in the universe grows from a 0 all the way to 10 to the 6 or 10 to the 9 solar masses. You always need a formation. You need to put together some mass. Typically, you reach some form of equilibrium for this object, typically pressure-supported objects and things like that. And then there is some instability that triggers the collapse of these stars to a seed black hole, and the seed black hole then grows all the way to its final size. Okay, so if you're interested in the dark matter distribution on scales larger than the supermassive star, then the previous model works very well. But because you are interested really in what happens around the supermassive black hole, we have to go through this series of steps. And to make a long story short, let me tell you what the final outcome of the calculation is. If you plot the dark matter density as a function of the radius, and this is for a 10 to the 5 solar mass object, you see that the ISCO here, or 4m in this case, is over the 10 to the minus, a few times 10 to the minus 8 parsecs. And this is the radius of gravitational influence. Sorry, this is the radius of the star that formed, that triggered the collapse. This is the size of the star that collapsed to a black hole. You see that, outside the star, it doesn't really matter how you form the black hole in the first place. If you are on scales smaller than that, and you do the proper calculation, you find something which is the resulting green here, which is a bit less steep and less dense than the calculation that I was showing before. Okay? So the difference is only a factor of 2, as a matter of fact, in this case. But we care a lot about these slopes here, because these are the ones that will induce environmental effects. And I will show you why this is important in a second. And you can actually continue this exercise and ask the question, what happens to the dark matter distribution as I continue to grow the mass of my black hole? And you can show actually that if you keep growing the black hole by orders of magnitude, you recover actually the results of the previous calculation. Okay, but we don't know really in nature what kind of objects we will encounter. So we need to be prepared when we analyze the data to all possibilities. Now the key question I want to ask, and I will spend the last 10 minutes of my talk on this, is how does the presence of an environment, in particular of dark matter, affect the gravitational waveform? All right? And the idea is quite simple. Suppose that you have a central object and another object orbiting around it. We know how to calculate the waveform, so strain as a function of time or of frequency, with very good precision. Okay, this is GR in vacuum. We know how to do these things. There are a number of details that we still need to figure out, to be able to perform proper statistical inference in the entire parameter space, taking into account interactions of spins and relativistic effects and so on. But we know how to do this. We've been doing this for decades now. What happens if I have dark matter? Well, what I need to understand is how the presence of dark matter modifies the orbits of the secondary objects. And I will mention in a moment the physical effects that induce this change in the orbit. And then I want to understand how is the waveform modified by the presence of dark matter, by an environment around the system. Okay, so this is our task. Why should we expect a modification in the orbit? Well, suppose that you're sitting on the massive black hole and you're looking at a companion that is orbiting around you in this direction, in presence of these dark matter particles. Well, what you can do is to calculate the dynamical friction that is induced on this object by the interaction with these dark matter particles. Okay, and this is really dynamical friction in the same sense that Chandrasekhar did in the 1930s. So you might say, well, okay, this is easy. This is bread and butter for a graduate student. You take the orbital energy, the energy losses are due to energy losses in gravitational waves. You just add one term that corresponds to this dynamical friction losses. And then for the evolution of your separation of the binary, you have one term, which is the emission of gravitational waves, and another term, which depends, it's linearly proportional to the density of dark matter, and that encodes gravitational dynamical friction. Okay? So you might say, I can do this. Problem is, let me show you like a numerical simulation to drive this point home more effectively. If you have two systems, so this is the case where you have two objects surrounded by dark matter, two black holes surrounded by dark matter. You let them interact, and what happens is that, as you will see, these objects, there's a very violent transfer of energy from the binary to the dark matter distribution. This is a purely Newtonian interaction between these objects. So in principle, these black holes should go back to their very elongated orbits where they started. But in reality, what is happening is that the binary is losing energy, and therefore it's reducing its separation and also becoming more circular. And if you look at the dark matter distribution, let me run this again one more time. If you look at the dark matter distribution, you will see that most of these dark matter particles are kicked out of the system because of this very violent interaction. You will see that after a couple of interactions, most of the dark matter around these systems is gone because of this transfer of energy. Okay, so the point I want to make is that you cannot solve the system in the simple way I just shown, because you need to co-evolve at the same time the distribution of dark matter and the orbits of these two compound objects. Okay, so how you do this? Well, you go back to your equation, but this time in the evolution for in the equation for the separation, you have a dark matter density which is time dependent, and you need to combine this equation, complement this equation with another equation that tells you how the phase space of dark matter evolves in presence of these interaction. All right, so with these two equations, you close the system, you co-evolve them. The solution of this of the system is way more complicated than the previous one, but can be done. And if you ask the question, so if this is the density of dark matter as a function of radius, this is the central object, and this is the companion that is merging with the central one, you will see that the dark matter distribution is time dependent because it's reacting to the presence of this companion. And you can basically, by running this type of experiments, you can calibrate the dynamical friction and derive the consequences for the dephasing in the waveform. So now if we go back to what I was showing you earlier, the leading cause of the dephasing is not the only one, but the leading cause of this dephasing is precisely dynamical friction. It's a very small effect, but it's a cumulative effect, right? And in principle, with LISA, you can follow hundreds of thousands, even millions of cycles in particular for extreme mass ratio in spirals, meaning that the compound object here is much smaller in mass than the central object there. Okay? So this was the starting point of this exercise, the realization that the dephasing, that in presence of dark matter, these waveforms get dephased. Now the question, which is the next and final question I want to ask, is this dephasing characteristic of the dark matter, or is this something that can be mimicked or reabsorbed by varying the parameters of the system or by the presence of other environments? Okay, so the first question was, can we detect, discover, or measure dark matter with gravitational waves? And what you can demonstrate, actually, so this was done by Adam Coogan and a bunch of us in Amsterdam. We can discover these systems for the fiducial values of all parameters up to 100 megaparsecs away from us. for these systems, we can tell that these are not GR in vacuum in terms of Bayesian model comparison. So there's no way of modifying the general relativity parameters of the system such that they would induce a dephasing like the one that is induced by these dark matter spikes. And we can also, if we see these events, we can measure the density profile and the normalization and slope of the density profile, and we even get a sense of the mass ratio of the binary itself. The next question is, okay, well, maybe if it's true that we can, as it seems to be true, that we can clearly discriminate this type of events from GR in vacuum, so we can say there is an environment around the systems. The other question is, can we identify the kind of environment that has produced this dephasing? So can we tell an accretion disk from a dark matter spike or from a gravitational atom? And well, I don't have much time to give you much details about this, but please ask me questions if you're interested. So to make a long story short, and this is the work done by, led by Pepako, you can ask the question, how well would I be able to reconstruct the parameters of a particular environment should I see its effects on a gravitational waveform, a measured gravitational waveform with LISA? And in all of these three different cases, accretion disks, dark matter spikes, and gravitational atoms, you can do full statistical inference and reconstruct the parameters of the binary and also the parameters of the environment that is inducing the dephasing. But what's maybe even more important is that you can really perform model comparison, meaning you can inject, you can create mock LISA data under the assumption that one of these environments is present around the black hole. So suppose that dark matter is present around the black hole. You produce like a mock gravitational waveform and ask the question, would I be able to reabsorb the effects that I observe in terms of a GR in vacuum templates, an accretion disk templates, or a gravitational atom templates? And in all cases we've tested, there is enough information in the data to immediately point to the right environment. In other words, the Bayesian evidence would be always in favor of the right environment, right? And the reason for that, if you think about it, besides technicalities, what is happening here is that these systems, especially these extreme mass ratio in spirals, are more similar to a particle physics experiment in a way, right? These two black holes are very similar to elementary particles interacting with each other in a similar way as to what elementary particles interact in your colliders. And you know your theory, the standard model of particle physics in accelerators, and GR in the case of the interaction of these two compact objects, so well that any departure from the prediction of the theory will lead to a potentially detectable effect. And what I wanted to show you here is that if you do the full exercise and ask the question, will we have enough information with LISA data to disentangle these different cases? Well, this paper here suggests strongly that this will be the case. And even if you don't think that, if you don't have a specific interest in any of these environments, it's important to remember that ignoring these environmental effects can bias statistical inference on the physical parameters of the system, bias chirp masses, and in some cases actually lead to a sort of a catastrophic loss in signal-to-noise ratio. Okay, so we've been working a lot, step by step, to try and understand the potential of this new strategy to probe the nature of dark matter. A couple of recent results: we have a fully relativistic treatment now of the compact object dark matter interactions. We've been exploring how we can use machine learning, and in particular sequential simulation-based inference for extracting the information when we analyze the data of extreme mass ratio in spirals. And we're also studying how the interaction with the environment can lead to interesting constraints on the nature of the companion. And I think in view of time, I will stop here. I think the most important message is that the era of precision gravitational wave astronomy is coming. Gravitational waves are very powerful probes of black hole environments, and this actually opens up the possibility. I didn't have much time to talk about this, but if you're interested, please ask me questions. The possibility to even investigate the particle nature of dark matter. So discovering the presence of dark matter around the systems already will be an incredibly important result, because we would extend the validity of our standard model of cosmology to by many orders of magnitude, really, in distance, and also validates the particle nature of dark matter as opposed to modified gravity. So we'd make it possible, really, to address some of the most important questions in the field. But even more, and we're working a lot on this, we can also hope to, if we manage to see these events, to extract information on the very particle nature of dark matter. Thank you.
Thank you, Gianfranco, for a fantastic talk. We have time for a couple of questions now. Gianfranco is visiting today and tomorrow, so feel free to reach out to him again. Yes.
So thank you, great, super interesting. So I had like two related questions. So I was wondering, first of all, in the realistic environment, the vicinity of black holes, my impression was that for most of these environments, the dominant contribution to the matter distribution would be baryons and not dark matter. And so would that make it difficult for you to identify signals of different dark matter models? And the related question is, have you also thought about like black hole decay at larger scales from like tens of kiloparsecs to kiloparsecs? Because there you have dynamical friction, which is for the most part dominated by dark matter, and it would not impact the gravitational signal because gravitational waves are not produced in that regime, but it could impact the overall event rates in the first place.
Absolutely. Two very interesting questions. Let me give you like a short answer, and then we can follow up. I can provide you with more details. Now, for the first one, maybe let me show you something like this. So our intuition is on the relative abundance of baryons and dark matter on small scales typically comes from how baryons are distributed in a galaxy like the Milky Way, right? We know that dark matter density dominates in the outskirts. If you go towards the inner regions, then you have this kind of opposite effect where baryons dominate completely the gravitational potential. That's certainly true. But that intuition doesn't tell you what happens on very small scales around the black hole. We're talking about tens, maybe maximum 100 solar masses, gravitational radii around the supermassive black hole. So we're talking about between 10 to the minus 6 and 10 to the minus 4 parsecs, say, around the supermassive black hole. Now, this is a region where you don't even have stars, right? The pericenter of the S2 star, which is the closest star that we know at the galactic center, is hundreds, almost 1,000 Schwarzschild radii from Sagittarius A star. In terms of disk, well, we actually know how the accretion disk around Sagittarius A star looks like, and we have an idea about its density and so on, because we observe it with the Event Horizon Telescope. And the density is not very high. It's actually a very dilute system. If what we think happens on those scales is true, the fact that you have this kind of relic population of particles, of cold and collisionless particles that are sitting there at the bottom of the potential of the Milky Way, well, then the growth of the black hole inevitably pushes their density to very high densities. Okay, so they can actually be larger by orders of magnitude compared to the density of baryons in the same region. And then, I'll give a short answer to your second question. Yes, it is in principle possible that the presence of dark matter induces a a dynamical friction that modifies the merger rates or the merger time of these objects. Numerical simulations, again, suggest that this is an effect, but not the leading effect, precisely because of what we were saying before. You typically need, to solve the final parsec problem, you need to have like a mechanism which is effective when the separation is much larger than the Schwarzschild radius of these two objects, because then, when that happens, everything becomes dominated by gravitational wave losses, and that typically is dominated by baryons at the center of galaxies. But we're working on this. We're running numerical simulations precisely to address that particular problem, but also things like, is there any evidence, for example, that there are self-interactions in dark matter particles, and how would they affect precisely the kind of observables that you have in mind?
Last very quick question.
Yes, I was interested in distinguishing between accretion disks and the dark matter clouds. So accretion disks can have various kinds of morphologies depending on the accretion rate. Like it can be razor thin, it can be puffed up. Analogous to the dark matter cloud morphology maybe. So what kind of range have you considered?
So for this particular, in this particular case, this was done for one particular type of accretion disks. It is in principle possible that if you generalize this to any morphology of baryons, the Bayes factors might be deteriorated because of the more complex structure that you allow baryons to have. But what's important to keep in mind is that in the case of dark matter, these systems, the prediction is the evolution in frequency of the D phasing is actually very, very simple, because it's dynamical friction, cold and collisionless particles distributed in an approximately power law distribution around the center. You would have to play very hard with accretion disk to mimic this kind of effects, to the point that, also because in the case of accretion disk, the leading effect is not dynamical friction. It's more like torques, like you have in planetary systems, essentially. And the evolution in frequency is completely different. So you would have to miraculously adjust the density of baryons and the type of energy losses to mimic exactly the kind of prediction that the dark matter have. You cannot rule it out in complete generality, this possibility, but it's so fine-tuned that I think it will be a very... And then let me mention another thing, and then I close. If you only see one event, it may be that you don't have enough information to disentangle the two. But if you see more than one, then you would have to do this tuning for each of these different systems, which becomes so desperately fine-tuned that I think it will be a very convincing argument in favor of dark matter.
All right. Let's thank Gianfranco.
Thank you.